number of very interesting talks about quenching of satellite galaxies. I'll be going to talk about quenching of massive central galaxies at redshift 2 and above. Okay, it's not working. Maybe better here. Okay, so when we look at galaxies in the local universe and now to redshift 2, 3, and even 4 now, we see that they come in two different classes. One are star-forming galaxies with young ages, blue colors often, and high specific star formation rates. And then, of course, we have this class called of quiescent galaxies, which have older ages, often red colors, and low specific star formation rates. And one of the big questions, obviously, is what is the physical origin of this population of quiescent massive galaxies at redshift 2 and above? All right. And in the literature, there have been proposed a number of quenching channels, such as internal mechanisms, such as morphological quenching due to the formation of a dense bulge in some galaxies. The quenching could be related to the chemistry of the interstellar medium. We now heard a lot about environmental quenching mechanisms, such as run pressure stripping and starvation. Feedback, of course, is often put forward as a quenching channel, either in terms of an ejective feedback mode, which blows out a lot of gas from galaxies, or as a preventive mechanism that reduces the gas accretion rate onto galaxies. And there are also heating sources that are not directly related to feedback, such as gravitational heating, infalling substructures, heat the gas, or the formation of virial shocks around massive halos, which lead to a quenching mode that is often known as the halo mass quenching. All right. And finally, I would like to add, another channel here, and that is related to the overall accretion history of galaxies and their halos. All right. And I like to call this a cosmological starvation. And what is it? Well, it's a period of reduced matter accretion, dark matter, and baryons onto halos. These lower good accretion rates lead to lower gas inflow rates into the galaxies, and therefore to reduce star formation rates. So the critical thing here is that the cosmological starvation is related to the dark matter halo growth history, so to the specific dark matter accretion rate of halos, and not to the halo mass. So I gave a talk last year at this very conference where I put forward some evidence for this picture based on a cosmological zoom-in simulation, the Argo simulation that I run with gasoline, and has all the standard physics, so normal kind of feedback based on a low density, blast wave feedback, no feedback from elective galactic nuclei. And the simulation includes one massive galaxy of about 10 to 11 solar masses or so, and has softening lengths of about 120 parsecs, and then a speech particle mass about 2 times 10 to the 4 solar masses. And one of the plots that we had in the paper is this one here. So it shows what the red curves are the baryonic masses, and the blue curves are the dark matter masses. And this is the halo mass, here the black curve is function of redshift. And you can see that at high redshift, the baryonic mass and the dark matter mass, they kind of co-grow. And then at redshift 3.5 or so, this stops. So the dark matter stops growing and the baryonic mass stops growing. And that's what I would call the onset of cosmological quenching or cosmological starvation in this particular example. Unfortunately, this is only one galaxy, okay? And it's of course very difficult to do statistics with just one object. So I joined the FIRE team, okay? And I'm collaborating with Elliot Credert, Phil Hopkins, and Dusan Karish, and other people on Massive Fire, which is a follow-up project to the Argo simulation. All right, so let me just give you a few stats. So we simulate 18 zoom-in regions in a large-scale cosmological volume. Each of the zoom-in regions has at least one halo in this mass regime at redshift 2. The simulation stops at redshift. The simulations stop at redshift 2, And overall, we have about 40 or so galaxies with a stellar mass above 10 to the 10. The resolution, the mass resolution is similar to Argo, so a few times 10 to the 4 solar masses is the resolution of our SPH particles. We have a much higher spatial resolution. The minimum gravitational soft length is about 10 parsecs. And the physics is essentially the standard fire physics. And we heard about this yesterday, so I don't need to repeat it. Maybe one point to stress again, these simulations do not include feedback from AGN. And this is a rather good orthogonal approach to large-scale box simulations such as Eagle and Illustris, which of course have a much larger number of galaxies to study, but at a much coarser resolution. Okay. So just to give you a little overview of the diversity that we have in our sample. So here I show the mass growth history of the dark matter in the simulations. And this is the large-scale good environment. Here, this model is, or just determined here, is the mass in some radius around the galaxy. And you see that there is really a large range in both halo masses, in the accretion histories, and in the environments. So this is the first look at our sample. Here I produced stamps, mock images, UVJ combined mock images of the galaxy, of the massive galaxies in our sample. I ordered them according to their UV and VJ colors, and this yellow line separates the star forming of here from the quiescent galaxies according to the standard UVJ criterion. And you can see that we have in our sample both quasi-quiescent galaxies and star-forming galaxies. And this is the face-on view. This is the edge-on view. We also have, I think it's interesting, we have a number of disks in our sample at redshift 2, and you can see this better if I remove the dust. So here. So we have a number of really large-scale disks. So each of the stamps is 30 kiloparsecs on each side. Okay, so just an example further. So this is a quiescent early type galaxies at redshift about 2. I mean, we run a few of these galaxies further down. Then this is a star-forming, a regular galaxy, and then this is a large star-forming disk galaxy. Okay, so this is a more standard UVJ diagram. As I said before, we have both star-forming galaxies and quiescent galaxies. This is the M star to specific star formation rate relation. Here I colored star-forming galaxies according to UVJ in blue and quiescent galaxies in red. And you can clearly see that, the UVJ diagram does a decent job in splitting star-forming galaxies, in splitting the galaxies with high specific star formation rates from galaxies with low specific star formation rates. And we also kind of really nicely could also reproduce the normalization and the scatter of the observed star-forming sequence at redshift 2. This is the stellar mass to halo mass relation at different redshifts for our sample. Again, there is it's a reasonable good agreement. The scatter is about 0.3 dex at each redshift. Again, this is not far off from observations. Okay, so let's now look into some examples of how individual objects look like. So here I just show you an example of a star-forming galaxy, and this is really kind of typical what we see. The gray band is the specific it's a star-forming sequence at that time for the mass of the galaxy at that time. Okay. And the blue line is the specific star formation rate of this galaxy. So you can clearly see it evolves essentially along the main sequence. But there are sometimes really large excursions from it. Okay? And here at the bottom, I show you bars where the filled bars indicate major mergers and the empty bars indicate minor mergers. And you can see, there's a lot of merging activity going on. And here, for instance, in this case, this is clearly a kind of an outburst that is related to this major merger. We see this also clearly in many other galaxies, yes, in our sample. Okay, so now let's look at a quiescent galaxy. And it looks very different. Okay, so the first thing that you notice is that its specific star formation rate is actually below the main sequence already early on. There are also still large good fluctuations. And then if you look at the merging activity, there's really not much going on there. Okay, so it has a couple of mergers at really high redshift and then essentially nothing happening. Okay. So just maybe that's just an interesting kind of trend that we find. If we group our galaxies according to the overdensity in which they live, we find that star-forming galaxies prefer overdense regions at redshift 2. And quiescent galaxies prefer underdense regions. And here, the density is measured within proper 2 megaparsecs, so which is kind of whatever, 6 co-moving megaparsecs at well at redshift 2. All right. So, all right. Now, let's look at the starvation or the cosmological starvation picture. And the first thing that I did was to fit the accretion histories or the growth histories of the halos, of the dark matter component of the halos, and the baryonic component of the halos. And well, let's just plot them here next to each other. More positive numbers means stronger dark matter growth, and a positive number here means a stronger baryonic growth. And you see, first of all, there's a nice kind of correlation between the two. Dark matter and baryons and halos co-evolve. Okay, that's not, well, essentially new. This has been known before. But the interesting question is now, what happens if you go from the halo picture down to the down to individual galaxies? So I will do now 2 changes. First, I will go from the baryons to the cold baryons, so stars plus H1 plus H2. And instead of measuring the baryons within our VIR, I will measure them well around the galaxy, so within 0.1 hour. Let's see whether we can still see a nice correlation between them, and that's what we get. So the answer is yes. So there's still a nice correlation between the growth rate of the halo, of the dark matter component in the halo, and the cold baryonic component in the galaxy. Okay, and now what I can also do is I can split now, or I can color code these points according to whether they are star-forming or quiescent galaxies. And that's what you find. Okay, so we see that if the halo is growing very quickly, then essentially these are all star-forming galaxies. You cannot be quiescent if your halo is growing quickly. So you need to have a slowly growing halo to be in a quiescent galaxy. These guys here, these empty ones, these are satellites. So they are essentially often on the negative side. So they are not growing, they are shrinking. The dark matter mass is shrinking, right? But the central galaxies, they are always essentially on the positive side. So they're always kind of growing or maybe essentially kind of stalling here. What's interesting, though, is there's this kind of region here where we have kind of both kind of star-forming galaxies and quiescent galaxies. So it's not entirely clear whether this cosmological starvation is sufficient to quench star formation, but at least from this picture, I think it's evidence that it is necessary. Okay, so, well, that's all good and well. Okay, so I told you that there's this co-growth between the cold baryons in galaxies and the dark matter halo, and that's the evidence. But this leaves us with one conundrum, right? So, well, I showed you before the stellar mass to halo mass ratio. It evolves kind of strongly, and if you really plot it, which I do here now, you see it's not constant, of course, right? So lower mass halos have a much smaller fraction of stars than more massive halos, and this goes up until you reach a halo mass of about 10 to the 12 or so. So what's going on here? I mean, what is breaking this coevolution between the stars and halos? And well, unfortunately, I don't have the full answer yet to that, but I can make the same plot where I show on this axis, instead of the stellar mass, I show the cold baryonic mass of the galaxy and divided by the halo mass, okay? And it looks like this, okay? And also show a fit. And you can see it's essentially good horizontal. There's essentially no change. So, which means that the cold baryonic mass of galaxy essentially is a constant fraction good of the halo mass. And if you want to understand now this trend here, it's really just something about the conversion of cold baryons into stars. So this is probably something related to the local feedback of the interstellar medium or to the star formation process in galaxies. All right, and I think that's all I have to say from a summary here, and I'm happy to take questions. Thanks.
Questions? Let's see. Yep. Can you go back to the picture where you had the UVJ diagram and all the different light profiles, the stellar light profiles? So it looked like you had the actual images from...
Oh, here. Yes.
So most of these look fairly round, right? Not disks, even in the star-forming population. Is that true? I see lots of gas, but...
Yeah, so so it's maybe clear to see if you take dust away. Okay, so that's how they look.
There's more disks. Okay, so in the quiescent population, you have both extended quiescence round objects and dense, compact round objects.
Yes.
What do you think the difference is in why they got to be that way?
Yeah, so in this plot I show both centrals and satellites. So some of the object that your eye is maybe drawn to, like, I don't know, this guy here and this guy, these are satellite galaxies. So they are typically round and kind of boring looking. The more massive ones, like this one or this one, they are typically, you see, they typically are not as round. So they are typically more elongated. You know, these guys here, these are, this guy, you know.
The top panel's all round?
Satellite, central. Satellite, central. Yeah.
Okay, for at the redshift 2, what's the gas fraction within this massive star-forming disk? That's the first question. And the second question is, are they clumpy in the gas? Are they unstable?
So the gas fraction, I don't know the exact number, but we looked at them and they look kind of reasonable, whatever, 50, 60%, something like this. Clumpy, well, yes, so there are clumps, we see clumps in this simulation, and you may even see that, you know, in these kind of images here. Whether these clumps are, you know, entirely physical or something, I mean, that's a different question. So, but yeah.
Here. So we now have some candidates for quiescent galaxies, massive quiescent galaxies at redshift of 3, 4. So do you have any galaxy in your simulations that form so many galaxies as 10 to 11 solar masses by redshift of 3 and then they dead 4?
So, okay, so we have 3 different halo mass bins. Our most massive halo mass bin, well, okay, short answer, no. Okay, our most massive halo. So the most massive galaxy in our medium and low mass bin goes up to 10 to the 11 by redshift 2-ish. Our most massive halo mass bin, Freedom 10 to the 13. It appears that all the ones that we selected by chance, because we have only 3 of those, they appear to all grow very quickly at late time. So, which means if you look at them at redshift 4, their stellar masses will all be very small. So we don't have these extremely massive kind of galaxies redshift 4. But I think if you want to study these, you really have to target them because they are so rare that you really have to set up your simulation specifically to target these kind of galaxies.
Last question.
So, Rob, apart from sort of calling it cosmic observation, I understand what you're saying is what is implemented in the so-called bathtub models that you know very well, which you're saying that the specific, you know, the star formation, the accretion of baryons scales with the accretion of the dark matter, and the puzzle that other people have tried to address is why actually the baryons are above the dark matter, so being faster than accreting than the halos and the dark matter, or actually a few. So I'm curious, in your simulations, given that you're presenting the same picture, what is the physical cause for this faster accretion of the baryons relative to the dark matter?
So I don't think we see it necessarily a faster accretion of the baryons. Do you mean just you know, within the galaxy or within the halo? Yeah. 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 Okay, so it's not really the accretion rate of the baryons; it's more the specific star formation rate. So that's a different thing. Yeah, so that's a good point, and we should definitely look into this. Yeah, I agree. And what is it? Well, it's a period of reduced matter accretion, dark matter, and baryons onto halos. These lower good accretion rates lead to lower gas inflow rates into the galaxies and therefore to reduced star formation rates. So the critical thing here is that the cosmological starvation is related to the dark matter halo growth history, so to the specific dark matter accretion rate of halos and not to the halo mass. So I gave a talk last year at this very conference where I put forward some evidence, bulge in some galaxies. The quenching could be related to the chemistry of the interstellar medium. We now heard a lot about environmental quenching mechanisms such as run pressure stripping and starvation. Feedback, of course, is often put forward as a quenching channel, either in terms of an ejective feedback mode, which blows out a lot of gas from galaxies, or as a preventive mechanism that reduces the gas accretion rate onto galaxies. Have this class good of quiescent galaxies, which have older ages, often red colors, and low specific star formation rates. And one of the big questions, obviously, is what is the physical origin of this population of quiescent massive galaxies at redshift 2 and above? All right. And in the literature, there have been proposed a number of quenching channels, such as internal mechanisms, such as morphological quenching due to the formation of a dense. And there are also heating sources that are not directly related to feedback, such as gravitational heating, infalling substructures, heat the gas, or the formation of virial shocks around massive halos, which lead to a quenching mode that is often known as the halo mass quenching. All right. And finally, I would like to add, another channel here, and that is related to the overall accretion history of galaxies and their halos. All right. And I like to call this cosmological starvation. A number of very interesting talks about quenching of satellite galaxies. I'll be going to talk about quenching of massive central galaxies at redshift 2 and above. Okay, it's not working. Maybe better here. Okay, so when we look at galaxies in the local universe and now to redshift 2, 3, and even 4 now, we see that they come in two different classes. One are star-forming galaxies with young ages, blue colors often, and high specific star formation rates. And then, of course, we